Yeah. Yeah.
Hello, testing, 1, 2, testing. All right, we'll come back to from the holidays. Hope you guys enjoy your weekend. So yeah, as was promised last time, I fixed this solution to the projectile motion. Where should I start? Skip. You guys, have you guys read about it? Not yet. Some of you read. Not yet. Okay. Okay, maybe just briefly say about it. Let you read it and then you can pick back to me. Okay, so last time we have a projectile motion, right? Okay, so we have a projectile motion, and then we try to find the maximum D. Yeah, try to find maximum D. So which angle for what angle alpha, we can make the maximum range of the throwing. But we started by finding what is dy dx, which is to find the maximum point of our projectile, which is a parabola. Okay. So similarly, these 2 points might not have any connection to each other, right? Okay, one is the maximum, and then one is the ending point of this parabola. But it turns out that RD, okay, the x coordinate of RD is 2 times the coordinate of Rn. Okay, this is what happened. Okay, so why it happens? Please read the explanation. And then there's one result here. Maybe it's useful. So the furthest point. Okay, so the conclusion is this. Okay, the conclusion. I don't tell you how you calculate first, but you first understand the conclusion first. So the conclusion is, if you make your projectile 45 degrees from the ground, okay, it is the furthest throwing, you will reach the furthest throwing point, okay, other than 45, okay, either greater or less than 45, it will be symmetric across this 45-degree projectile, okay. So for example, there's a 30-degree and 50-degree point where they throw to the same throwing point, but they differ in the maximum point. Yeah, away from 45 degree, your range will be less, and your maximum point is also less. I mean, in the x direction. Yeah. So if some of you have trying to solve some question from the textbook, right? They also throw some fireball to the city, something like that. Someone shared to me. Seng shared to me. So there's a 2 wall. So if you want to throw over the 2 walls, maybe you have 2 degrees that you can throw at to reach the 2 places. I mean, to reach 1 places, you have 2 degrees. So yeah. Okay. So 1 degree is above 45, 1 degree is below 45. The reason is because of your projectile formula. Your projectile formula for x is sine. Okay, sine 2x is symmetric away from 45 degrees. Do you get me? So what's sine 2x? Sine 2x. So your sine 2x is like this. Okay, so you can see that away from pi over 4, so it's symmetric. Okay, this is the x coordinate. So maybe I use this. This is the x coordinate. Okay, but for y coordinate, it is sine square theta. So this one is increasing. 0 to how many? Okay, makes sense. These are coordinate of the projectile. So the x coordinate is symmetric away from, which is 45 degrees. Any question? Any question? Any question? No? Okay, next week have tests, so please be prepared. Until chapter 13. Is it 13? Which one? Which chapter? 10, 12, 11. No, 11 is 13, yeah. 10, 12, and 13. 10, 12, and 13. Should be next Tuesday, if not wrong. What? Thursday. Thursday holiday again?
Yeah.
Next Thursday holiday again? Oh, then we need to fix replacement again. So when's the you guys, okay, first of all, you guys want to do physical or online? What? Online? Okay, maybe we vote online or physical. For class. Class is Thursday holiday. What's the holiday? We start there. Yeah, what's the holiday? Yeah, it's we start there. So okay, so maybe we need to fix replacement. So how many of you want to do online replacement? Can I see the hand? How many of you? So we follow majority. Online. Who want to do online? Let me see. Can you raise higher? I want to see how many of you. Only majority, then we'll decide online or physical. One more time. Seems no more. 1, 2. Physical? Yeah. So majority is physical. So when you guys want to do physical? Wait, let me think. This is BSc, huh? Okay, when you guys want to do BC physical? When are you free? No time, What? Thursday morning. Thursday morning? No, the following Thursday. or this Thursday, following Thursday. Yep. Or maybe 8 to 10, 10 to 12. So physical one what time? When do you? Anytime? At what time? No, you need to mention the time. Okay. So let me pick a date. So you want to do it this week or the following week? This week? This week, the following next. Okay, the next one week. So maybe we fix the week first. So we fix this week, 8, 9, 10, 11, 12. So which day you can make it? Thursday afternoon. Thursday afternoon. No class. 3 to 5. 2 to 5. Yeah. Let me see. I got what. Tuesday afternoon. Afternoon,
拿白纸来做 quiz 就可以了嘛。那个白纸课来做 quiz 就可以了嘛，你就损失1个小时吧，只是损失1个小时。没有道理。下个星期
No. I mean.
你就这一次特别快。
Okay. Wait, we want to fix the physical class now. So you guys can make online or physical? If physical, you don't have time. No, I mean. No. Not talk about class. Talk about class first. Okay.
And the 2-hour things.
Okay, so we need to fix the day. Physical. Which day you guys want? So Tuesday afternoon. Fifth. Wait. So we fix after we start there, a week after we start there, right? So 9th May. 9 May, yeah. 9 May. 9 May. Yeah. 9 May. Afternoon. Afternoon. So we got class until 11. Until 6. Okay. How about Wednesday morning? Wednesday cannot. Okay. Thursday afternoon. Friday morning or afternoon? Afternoon. Okay. After 1. What time? After 1. 19. Sorry. 12. Sorry, 12. 12 May. If you want Friday this week also can if you want. Cannot. Okay. Another replacement. Okay. On Friday after we start day also can. So the time is 1 to 3 or 2 to 4? 1 to 3, 9, 5th or 12th? 5th, 5th cannot. 2 to 4. Huh? What? Okay, yeah, I also got class until 1. Huh? Straight away continue another class. 1 to 2 to 4. 2 to 4, 5th or 2nd, 12th? 5th or 12th May? 12th, huh? 12th. 12th, huh? The midterm, huh? week 9. Where's the week 9? 23rd is week 9? Yeah. So where's week 9? 1, 3, 4, 5, 6, 7, 8, 9. Oh, still got time. Okay, it's okay. So 12th May 2 to 4. 12th May 2 to 4. Huh? What are you? What do you have? Are you from AIT or no?
Yes.
No, I'm asking other. You are not from AIT, right? CST, huh? Friday, what time you like? An afternoon. Night? Huh? Okay. 4 to 6. But so there's another. So CST got class. So you guys want to do 4 to 6? Okay. 12 May 4 to 6. Okay. Physical. 12 May 4 to 6 physical. I need to book venue first. So
Monday 6 to 8.
Fix Friday already. Fix already, Friday. Okay, Friday, 12th May, 4 to 6 p.m. Physical. I need to book the venue.
You will email us, right?
Yeah, definitely. I'll make an announcement on Moodle, then you will get the email. Okay. I think you guys getting warm up already. Okay, so before we start, let's try to do one exercise first. Okay, try find the general term of the following sequence. And discuss about this. Discuss about this. This question here. Anyone try out already? Try out. What's your answer? -1. Power. Okay. And then? Okay. 5 over n. So n running from where to where? Starting from 1. Okay. So remember how we think about sequence? What's the basic sequence we have? 1, 2, 3, 4, 5, and so on, which is the natural number. Okay, so how we relate the natural number to this sequence here? So first of all, you can see that this sequence has alternating minus. Okay. So to get the alternating minus, you can take power of -1. Okay. When it is odd, power of -1, you get minus. When it is even, you get positive, right? Okay. And then you should observe that the numerator form a pattern. 3, 4, 5, 6, 7. So it's like a natural number but shifted. Okay, shifted by 2. At the denominator, what happened? You got 5, 25, 125, 625, 3,125. So what are these actually? So these are just the power of 5. Okay, so you got 5 to the power 1, 5 to the power 2, 5 to the power 3, 5 to the power 4, and so on. Okay, so when we put these pattern together, we will get this general formula here. Okay. Anyone got any other idea? So if you want to start with 0, okay, you can. Then you need to shift your index. But I think for our class, we start from standard. But if you want to start from 0, then you need to change your index. Okay? Is it okay? Okay. Okay, next. Okay, so now we have seen a few examples of sequence. So we want to think about whether the sequence converge or not. Okay, so meaning, does this sequence stay constant or arbitrarily close to some number? Okay, so for example, maybe I give you an example first. So I give you an example. So let's say we have a sequence. Okay, what we do is like 1.01, 1.0001, 1.00001, 1.00001. Okay, keep doing. Like, I don't know. It seems like there's something to do with this table. Let me rejoin. Okay, let's take this sequence here. 1.01, 1.001, okay, 1.0001. So you're adding 0 each step, okay, to the decimal place. So this number here, this sequence here, will get arbitrarily close to 1. Okay. And so this is one of the property we want to find. So let's define it. So we define a sequence to have a limit, okay, to have a limit. Let's call it L, or we say converge, limit, or converge to L, where we write lim n to infinity, an is equal to L. If the values of an get arbitrarily close to L, okay, when n is large enough. Okay. So what does it mean by arbitrarily close? Okay. Arbitrarily close is as close as we like. Okay, so for example, in this example here, okay, how do you know this sequence will converge to 1? What's the idea? Well, what's the idea make you think that this number is getting closer and closer to 1? Any idea? Any idea? Smaller and smaller. Okay, maybe smaller and smaller can go to other number, right? So why is it 1? I mean, why not I say 0 here? Why not I say 0? It will reach 0. Why it will reach 1? What do you mean by reach 1? It also won't reach 1, right? So how close? So what do you mean by close here? Okay. So how do you make this closeness idea precise? Right. So it means that no matter how close to this 1, right? So for example, you want it as close as 0.000025. Okay. You can find another number or term in this sequence which is that close to 1. Okay, so let me write down what I mean. So let me write down what I mean. So arbitrarily close to 1 means I can find a term in my sequence. Okay, I can find a term in my sequence such that let me put another am minus 1 is less than, we call it a number. Let's call this a number, okay? I call it epsilon. Okay, for any number in the real number, okay? So you want to make it 0.1 close, okay? I can find one. I just take the first one, right? If I want to say 0.1 close, right? Let's say we want to find 0.001 as close, right? So maybe I can take the third one. Okay, and then you can keep going, keep doing this. Okay. Okay, so this means by arbitrarily close and then limit. Yeah. Okay, make sense? Make sense? Any question? Okay. So for example, just now we said that 0 is not limit. Okay, it never reach. Okay, what do you mean by never reach? So mathematically means if I take a distance, there's no more term appear within that distance. Right? Okay. Let's say we take, for example, if we take 0.5. Okay. Does there exist an m, okay, such that an minus 0 is less than 0.5 or not? Does there exist the term in the sequence such that take away 0, it is less than 0.5? No, right? Because all these number minus 0 is at least 1. Okay, so they are at least 1 further away from the number 0. Okay, so it can't be the limit. So to be a limit, you need to be forever, you can find some number that's as close as you want sequence to the limit. Okay. 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 Another thing is I don't want you to confuse with the calculus one limit here. Okay. So the limit here, right, is taking discrete number. Okay, discrete number meaning you are taking 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So they are like distant between these numbers. But in calculus one, you do real number, right? So real number is continuous. So it's like a chain. Not a chain, I mean, it's continuous. Okay, so this is the two different you need to differentiate. So in sequence, it's discrete. In function, it's continuous. Okay? Okay. Okay, next. So how you picture this thing, okay? So you should picture this. So this is our team for the course. Similarly, you can put two axes. Okay. Remember that sequence is a map from natural number to real number. Right? So let's say this axis is n, this axis is real. Okay, so you start with 1, 2, 3, 4, 5, 6, and so on. Okay, so even though I draw this axis, right, I only care about this discrete point for now. Okay. So for example, what do you mean by limit to some limit? So maybe this this sequence will look something like this. Maybe jumping around. Okay. And then when it converges, it will be as close as together to a certain point. And then the limit will lie around here. Okay, you can see that this sequence will be getting as close as possible to this line. Then we'll say that this sequence converge. Okay, yeah, this is the picture of a sequence converging. Yeah, so far okay. Anyone lost already? So far okay or not? Okay. Okay, so Let me ask another question. Okay. If you are arbitrarily close to one number, does it mean that you are equal to that number? No. No, right? Okay. So do you have an example? Huh? Do you have an example? Quick example. So arbitrarily close to L doesn't mean that you need to reach the term. Okay. But if you reach the term, it means that you are arbitrarily close to L. Right? Because their distance is already 0. Okay. For every n greater than it. So one classical example from this calculus is this ex function here. So you have an asymptote at where is this? Y equals 0. Right? Then you are as close as possible to 0, y equals 0, but you never reach y equals 0. Okay. Yeah. Okay, so the definition we mentioned just now have some defect. It can't help you to find limit. Okay, because we don't make precise what it means by arbitrary close. So we need the following theorem. Okay. We won't prove it, but we need this theorem. So we will get help from calculus. So let's say, okay, let's say we turn our sequence into real function. Okay, instead we putting number, natural number, we put real number. Then it become a real real function. Okay, right? So let's say we know the limit of this function. Then we will also know the limit of the sequence. So this is the first tool we have to find a limit of a sequence. Okay. So let's take an example. Let's see an example. So for example, we want to find the limit of 1 over square root n. Okay. So to find the limit, you first need to understand the sequence first. Okay, what's the sequence here? Okay, what's the first term you have? What's the first term you have? 1, right? Okay, 1 over square root 1, which is 1. And then 1 over square root 2, which is 1 over square root 2. And then you have root 3, root 4, root 5, root 6, and so on. Okay? So what's your guess, the limit of this? 0. Okay, you see that it's decreasing. So you think that it's 0. So how to prove it? Okay, how to prove it? So we need to use this theorem here. Okay, we need to first look at the real function defined by this sequence. Okay, so what do we mean by that? Graph again. Okay, so we have 1 here. Oh, we have 1, okay, and then 1 over root 2, 1 over root 3, and then so on. Okay, so we think that it converges to 0. Okay, so how to show it? So we need to turn it into a real a function, sorry, just says a function from real to reals. Okay, so pictorially, this means that we consider the continuous function. Okay, so we continuous. So do we know this limit here? The question is, do we know the limit here? Okay, so not that there's some subtlety here. Okay, so here we use n, here we use x. Okay, we want to differentiate the domain we take. Okay, when we put n, usually this n live in natural number. When we take x, x usually live in real number. Okay, so this we should know that this is 0. This is from calculus 1. Okay, so the theorem is, if we know the limit of the continuous function defined by the sequence formula, then we will know the limit of the sequence. Okay, so remember that 1 is a limit of a continuous function, 1 is a limit of a discrete function. Okay, from continuous, you can deduce something in discrete. Okay, okay, so next we should make a conclusion. So conclusion is, then by theorem, limit of the discrete sequence is equal to 0, since the continuous limit is also 0. Okay, not that I use n and x here. Okay, I use n and x here. Any question on this this part? Okay. Okay. So how about next? Next. Let's look at another sequence. So let's look at the alternating 1 and -1 sequence. Okay. So try and determine whether this converges or not. Okay. Then if yes, converge to what number? So does the sequence of alternating 1 and -1 converge? No. Why? Why? Yeah, the question is why. Huh? Yeah. Who is saying? Also oscillating between. So they are what? They are divergent. Okay. Sure. Actually, we haven't defined what is diverge, right? We only define what is converge. Okay, so let me return here and say what's diverge. So we just say converge to L if it get arbitrarily close to L when n is large enough. Okay. Let me put more in this definition. Otherwise, we say that the sequence diverges. Okay, so diverges could have a few conditions. Either it goes to infinity. Okay, because infinity is not in real number, so we are not considering infinity in our case. Or it doesn't exist, so you cannot find an L in R. Doesn't exist. Actually, they both characterized as the same because if it is not in R, it doesn't exist, right? But yeah, we can split into these two main cases, although they really stay in the same category. Okay, so would that say it diverges? Okay, so let's plot this point out. Okay, so that we have something to imagine. We have a 1 and -1 here. So we have, sorry, we start with -1, right? So when n equals to 1, n minus 1 to 1 is -1. So 1, -1, 1, -1, 1, -1. Okay. So this doesn't seem to that converge or diverge to infinity. So the limit doesn't exist. So can you make more precise why this limit doesn't exist? Okay. So first point he made is since the sequence oscillate between -1 and 1. Okay, it diverge. Okay, can you make it more precise? That is what. Okay, when I say I want to make it precise, right, you need to go back to your definition. Okay, what does the definition say about limit? Yeah, you need to make it arbitrarily close to L when the n is large. Okay, so in this case, okay, you haven't learned discrete math, right? So the logic here is you need to take the negation of that statement. Okay, meaning that meaning what? Meaning that if n is large, you also cannot make it as close as possible to a number L. Okay, this is the logic. So that is we cannot find a number L which is made arbitrarily close to all the sequence for n greater than some n. Okay, wait, I'll explain this. So picking large enough and okay, I'll explain this, don't worry. So we cannot find an L, okay? So let's say, for example, okay, let's say we pick an L. Maybe we pick 0 here, okay? We pick 0 here. We can see that no matter how far you go, okay, maybe number 3, number 6, or number 8, or maybe number 1 million, okay, you still cannot make that number as close as possible to any of your sequence. Okay, make sense? Okay. For example, let's say we pick L equals to 0, right? So let's pick L equals 0. Okay. We cannot make the sequence, the term of the sequence as close as possible. So for example, we pick 0.5. Okay. There's no term in the sequence that's 0.5 away from the limit. So we cannot do it. So maybe you will say, how about let's take L equals to 1. Okay? L equals to 1. Okay, let's pick another L. So let's pick L equals to 1. L equals to 1. Okay? Although we can find term that's close to 1, okay, fine enough, but we also can find term that is far away from L. And L equals to 1. Okay. So this doesn't work. So we want to show that we need to find for every, after a certain n, okay, all the term will be as close as possible to our limit. Make sense? Any question? Okay, maybe we take a question before we take a break. Yeah, take a question before we take a break. We take a question before I take a break. Okay, so sure. So let's conclude this example first. So this sequence diverges. So there's another question. So let's say if you, what do you mean by moments here? Say again. Okay. So maybe it oscillate, but got damping, can. So damping, something like this. Okay. So, but you can see that this still converge to a number. So oscillation is really not the issue here. The issue here is you cannot find a L which is arbitrarily close to your sequence when your sequence go very far. This is the issue. It's not the issue of oscillating or what. Okay. Hmm? Yes. 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 Sign on that. Yeah. Yeah. Huh? What? What? And what? Okay. Yeah. So oscillating is not an issue here. So okay, I mean the real definition of oscillating must be constant, but up and down is not an issue. But the issue here is whether you can find terms in sequence that's far away, far enough, which is close to your limit. Okay. Any more questions? Okay. Actually, there's one observation I want you to make here. You can see that here, actually, you can split into two obvious sequence here. Right? You have two obvious sequence here. Okay, I don't make precise. See if you can see it or not. You can see that I can make two sequences here out of one sequence. Okay, you can see that if these two sequences converge to the same limit, then you will have a limit. Okay, so for example here, the alternating -1, right? If I take the top sequence and the bottom sequence, they converge to different things, so they don't have a limit. That's a precise term for this limit. We call it a lim sup and lim inf, but we won't touch it here. Supremum and infimum. Okay, if no question, then we will take a break until 9:07 and then we'll come. Yeah.
就是你导问你那个，
Yeah.
其实我觉得想一下哦，其实也是我的那个概念，因为你看哦，你想看你刚才 你讲那个东西是
Yeah
如果像刚才你讲，你看那个图，你那个图
炸弹
啊，对对
，OK
对，
OK
就当你有一个图，
Yeah
你可以这样，你可以这样，
OK
对，也就是说，你看啊，假设我现在在打这个，
Yeah
我这样去攻，
Yeah
其实也是它也是一个范围，所以
啊
我觉得一个不是在那个范围那边，我觉得叠法应该是一样的，只是这样讲给解释就
没有，现在是什么问题？
没有问题
还有什么问题？
我想清楚，我只要跟你讲我想清楚。
然后你想清楚了什么？我刚才觉得我没有什么问题，你也没有什么问题啊，我觉得。
没有，只是
我觉得你也没
没有，
有问题。
我觉得等于，我觉得如果写
你觉得
等于
我有什么问题？
不，我觉得写等于很奇怪啊。
等于
因为如果我写等于的话，我是找到一个值，就是说，当我去找它，就是我要去打这个墙壁，或者是打后面那个墙壁。
对
但是如果我写一个 range 的话，是那个范围，就是说我可以这一个范围，
啊
对，合理。如果我只写等于，就是说，一个我打这个墙，或者是打这个墙。
啊对
但是如果我写一个范围是这两个墙之间，我都可以打得到，
啊 OK 好，可以，
合理吗？
我觉得合理，我觉得合理，我觉得合理，我觉得合理，
合理。
我觉得 OK，我觉得 OK，
OK， 行。
我觉得 OK。
就是如果写等于的话就给人的感觉就是我打这个墙吧，或者打这个墙。是，要是我写一个范围的话，
但是好像你真的去解的时候，你解那个点，
我也是写等于啊。
不是你解那个点的时候，它好像那个 degree 不太对哦，是吗？
我不知道，
它好像两个不会 match 到啊。你要 take 一个 range 哦，好像看到那个答案，你算过了？
答案是一个人，我还没有算，我还没有算。
不是，我是讲你算 x 的时候，好像他会给你一个 range，你算 y 的时候，他又给你另外一个 range，然后它会有一个重叠的 range，就这样。
哦，
对，所以意思说啊，你不小心设歪一点，呀，就是说，没有，我觉得你等一下算答案的时候，不是，他会已经把你包含一个 range 进去。哦，你先算一下你。
OK，
它好像会包含一个 range，它就天生不准。
因为我一看到的时候，我就是直接写 range，所以
你那个是设成的 range，我是说它的那个 domain 会有一个。
哦 ，OK，我回去试试看，试试看。
就 OK 啊，有点你要设到 CD 中间，我觉得也是。
可是也合理嘛，就你去打一个城，你不可能只把打墙壁打一遍的。
不是讲你不打墙壁那边，就是说他想要炸，因为你看啊，你炸城啊，它比较难弥补，你比较集中啊。
可是你
我觉得
炸城，可是你炸城的话，
比如你看荆棘的巨人
，OK，你讲，
就是他就是破城嘛，他不会可能因为我整个人这样跳进去嘛。
可是你放这个炸弹的意思是就是说你要炸到那个墙，对，它很难没有，但是它有一个可能性是，如果我还可以打到进去，所以为什么以前人他们打仗的时候，你没有看我们都是拿一个绳子在砍嘛，他们没有算了，他们就砍到，
打不
他们就是一个绳子那样子抓，把那个绳子，然后他们直接砍，大家好，这样子
啊，
所以他们没有算了，他们就这样子射进去是，他们就是要打到那个灭火，他们有火，对，那个墙有火是，
对，
但是他们会掉进去，就像你讲，他们会掉进去，那火会掉进去，所以他们会烧到中间。所以如果我一个可能我直接打到进去的话，我里面直接着火，然后那些人会在外面，会在外面的话，他们也是没有地方可以进回去啊，可以啊。虽然讲起来有点乱，但是跟那个有什么关系？
你就炸里面，那意思就是炸里面罢了啦。
对，
我觉得可以啊，我觉得可以，我觉得可以，
我觉得道理吧。
我觉得炸里面，
就那个
可以炸里面。
我回去试试看。
好像你在讲的是那个刚刚你讲那个sin delta 跟 sin square delta。
哦。因为它 formula 算出来 x coordinate 是长这个嘛，有这个成分在，然后 y coordinate 有这个成分在，对不对？记得吗？看一下，有。哎，这个，其实那个 RD 是2倍哦，这个东西就对了，所以它们 formula 是一样的，一个是 sin 2 theta，一个是 sin square 2 theta，虽然有这些 constant 在了，不重要，这是 constant 嘛。但是我想强调的是这两个 curve， 你看一个是 sin 2 theta，一个是 sin square theta，对吧？OK， 所以你看你的domain 有什么？从0到 pi over 2。OK， 所以你看啊，这个 sin 2 theta，sin 2 theta 是长这样，就是 symmetric away from 45度。OK， 所以是说你少过45度这边，多过45度这边，它们丢的地方、停的地方都是一样。你看 away from 45度，它都是比较越来越低了，而且它又 symmetric。OK， 所以它差别在哪里？它差别是在这个 y coordinate。你看 y coordinate 的话是 sin square theta，sin square theta 的话其实跟 sin 没有差很远，它就是 increasing， 0到 pi over 2它都是 increasing 的。所以你看啊，它才会造成了这个结果，就是说，虽然呢，它 maximum point 是一直 increasing 的，但是你看啊，它的那个 x 的点啊，其实是一模一样的。所以意思说啊，你丢最远的这个45度啊 ，away from 它啊，你不管是再往上一点呢，还是你再往下一点呢，其实你丢的地方都是一样的。虽然它会比较高，但是下来的地方都是一样的。这是它的结论。这个当然是没有考虑那个什么 air resistance 啊，可能你丢上去 air resistance 会比较低的，还是什么这样，会比较高啊？看你，
所以它这个degree 影响它，可是它，哎，就是我从任何角度丢，它一样还是会 reach 这边的。
就是会有一个对应的点，也会丢到同一个地方。一的多余或少于都有一个点会丢到同一个地方，可以 make sense 吗？你看嘛，你看这个，你看这个，你看这个，这个是 symmetry 的嘛 ？OK， 你看，如果你丢少于这边，多于这边，他们会丢到同一个点，对不对？
不知道，我刚来。
你看，对吗？你看，多于 pi over 4这边，少于 pi over 这边 ，OK， 他们两个点都会丢到同一个 x， 但是哦，它们的高度当然就不一样了，因为我们的 y coordinate 是 increasing，OK， 所以就会造成了一个就是这个 conclusion 哦。可以吗？你会觉得这个结论不合理吗？
有一点不合理，可是
为什么呢？你说说看。它确实是不合理的，因为这个只有重力的影响吧。如果你有考虑到那个什么 air resistance 啊，那种阻力啊，这样就不一样了。但是如果只有重力影响，它是这样的结果。最远呢就是45度啊，多过它少过它，你都是少。虽然你丢很高啊，没有用。
OK， 我以为你这个是45度，
哪一个？
我以为你这个轻车这个先
没有
，OK， 我懂了。
对，
因为你丢远嘛，你要一个是时间，第二个是水平速度。你第一个你的丢出去的时间一定要越长，然后你的水平速度也要越大，可能就丢得更远。是这样吗？你不是一定丢得越高越好，因为你假如你丢得很高，但是你的水平速度只有很小，你也走不了很远嘛。
没有，这个是在你控制，就是你的速度是，
我知道你的
固定的
速度不，你要分成水平速度和垂直速度啊。
是，但是这里把那些因素都固定住，然后考虑多少个角度。
它角度不一样，你的垂直和水平速度不一样。
OK， 你要那样子说也是可以
啊，
你要这样说可以，是这样说，但是是这样说，但是我们怎么说呢？对，
对，
对，
是因为就你分到两边，就是
通常我们说调起始速度的时候，我们就不调角度了。虽然说那个角度会影响你的那个什么 horizontal，
对，其实是差不多了。
对。OK。
这样它这个 equation 是我们本来是有一个是 parametric 的嘛，是 x 等于x 等于
parametric 啊
x 等于 v cos alpha t，那个是 parametric 的还是？然后这个是它
vector function。vector function。
哦 vector。哦
vector function。Yeah. vector function。OK。
那个不是刚刚那个讲那个什么趋近一个值吗？
对
它如果不趋近的话，它是有两种情况，一个是摇摆的，还
对
有一个就是趋近无穷大或无穷。
对，是没有错。Hello, testing. Daniel, is it Daniel? Just now you want to ask something? Already asked him. Okay, so you said that. Okay, good. Yeah, let's put down this this. Okay, so we just now we got the first two, right? Okay, so make sure you keep your two in your cheat sheet. So just now, I mean, how to find the limit, right? So make sure you know that too. So you can use the limit of continuous function to find the limit of sequence. Okay, yeah, keep it down. Will be very useful. For now, no. Yeah, for now, no. Yeah. So yeah. Okay, so we will introduce another tool. Okay. Next tool will come in handy. So it is the properties of limit of sequence. Okay, so to use these properties, right, you need to start with one condition. Okay, so let an and bn be convergent sequence. Okay, so let's say we already know they converges. Okay, and then we know where they converge to. Okay. Let's say we fix one constant first. Okay. Later we will use it. So fix one constant. And then we start with two convergent sequence. Okay. So one obvious thing is what's the limit of a constant number? What's the limit of a constant number? It's just C itself. Okay, because we can make arbitrary close to C for n large. For n large, it is still C. Okay, C minus C is 0. Okay. How about next? Let's say you know a sequence converges. Okay, you take a sequence, any sequence you can imagine, and then you multiply a number to all of them. Okay, and then you can ask, what's the limit of the new sequence? Okay, what's the limit of this new sequence? It will be just C times the original limit. Okay. What about if you add or minus two convergence limit together? Okay, so you want to find the limit of the new sequence. What do you think? You can multiply the limit inside. Okay. So actually this property, right, might not always be true. Okay. But when these are true, it is linear. Okay. Normally, usually when it is linear, you can do this. So this limit, this property, right, not always true. Okay. But for limit, it is true. Okay. So similarly, you can multiply two terms in your sequence. Sorry. Okay. And then the new limit will be just the all limit multiplied together. Okay. So this is kind of natural. So similarly, you also can divide the sequence. And then you will guess that actually the limit also divide themselves. So be careful that you have division, right? You don't want your term to be 0. So if you learn linear algebra, right? So one remark you can make is so the limit is a linear operator on the what's the vector space? The space of convergent sequence. Okay, maybe you need to restrict the space, but we'll put it like this first. So how to use this formula? So let's give an example. Let's give an example. Okay, so find the following limit. Square over 7n squared plus 1. Okay. So you can try and play around with this sequence first. So if you try substitute n equals to 1, 2, 3, 4, 5, you'll get 3 over 8, 12 over 29, 27 over 64, 48 over 113. So is this obvious that where this limit or even whether it converges or not? Is it obvious? Okay, if it is obvious to you, then you are a genius. I have to ask you how to see it. Okay. So what do we do? Okay. So we can simplify this sequence first, actually. Okay. So what we can do is the normal calculus trick. Okay, you divide and square on both sides, multiply by 1, right? If you do this, so what do you get? You get 3 over 7 plus 1 over n squared. So this is just another expression for your sequence. Okay, but this formula here is relatively easier to work with. Okay, so just now I told you how to combine stuff, right? If we know an converge, bn converge, then we will know when so we can find the limit after we combine the sequence. Okay, so now you got a combined sequence here. Okay, so how you split them into convergent sequence? How you split them into convergent sequence? Can you split them into convergent sequence? Do you get my question? No? Okay. So just now, from this property, right? Okay, I teach you how you go from AN, BN, and a constant C, and then build a whole bunch of sequence here. Okay, so you start with a sequence. Yeah. So for example, so just take one example, right? So we have our running example 1.01, 1.001, 1.0001. So we know that these converge to 1. Okay. So we can take a C, maybe 2. So we consider 2 times 0.02, 2.002, 2.0002. Okay. By this property here, it converges to 2. Right? 2 times 1. Yeah. Question? Huh? Say again. The screen what? The screen what? Not moving. It show everything I wrote. I wrote something here. Yeah. Okay, it's okay. So if I multiply 2 to this 1.01 sequence here, right? I also get the limit as 2 times the previous limit. Okay. Can everyone get this? Everyone get this? Okay. So similarly, you can add sequence, multiply sequence, or divide the sequence, and then you get the corresponding limit just by adding or multiplying or dividing, right? Make sense? Okay. So now my question is, if I start with some combination of sequence, can you split them into convergent sequence? Okay, so that we have this condition here. Okay, so now the question is, this is our sequence now. Okay, 3/7 plus 1/n squared. Okay, so can we split this term into convergent sequence? Huh? So how many sequence we can split into here? Huh? 3. We got 3. We got 7. We got 1/n squared. Okay. So the next question is whether these atomic sequence are converging or not. Okay. So first sequence converge or not? Converge to what? 3, because it's a constant sequence. Because the first rule of the property is limit n to infinity of a constant sequence is just that number. Okay. So this one converge to 3 equals to this by number 1. Okay. Similarly, you can see that 7 also converge to 7 by number 1 as well. Okay, how about 1/n squared? Does this converge? Converge or not? Converge to what? 0. Why? The graph. Okay. You could plot the graph, but you need to look at the function from the continuous function defined by 1/x squared. Okay. So you look at the continuous function defined by 1/x squared. Okay. So since limit of x infinity of 1/x squared is 0, okay. So since we know the real function limit, then by the definition, by the theorem, the discrete limit is also 0. Okay. Can get it? You guys get it? This. Okay. Once you know the limit of your continuous function, you will also know the limit of your discrete value. Okay. So this one converge to 0 when n go to infinity. Okay. So you have 3 converging sequence. Okay. So you have 3 convergent sequence. Right. So to find the limit of 3/7 plus 1/n squared. Okay. By the property of the limit of sequence just now, limit of sequences. Okay. So if you want to find the limit of 2 sequence dividing, is just dividing the 2 limit. right? Okay. Following. Okay, then continue. So if you want to find the limit of the addition of two sequence, it's just adding the limit of the two convergent sequence. Okay. So since we know that these three are all convergence, we know where they converge to. It is just 3 over 3 plus 0, which is 3 over 7. Okay. Okay, Adam. So the skill you need here is whether you can see these sequence are converging sequence or not. Okay, and then you can find their limit and then try to put them together using the property. Okay, easy. Easy or not? Okay. Okay. Next. Okay, next. So next, let's check. Does this sequence converge or not? Yeah. Leg again. Okay. Let's continue. So how about this sequence here? Maybe I let you try first. So let's take this sequence. N over square root e times n plus 2. Okay. Check whether this converge or not. I'll let you try for 3 minutes. Okay, try check whether this sequence converge or not. N over square root e times n plus 2. Okay, any idea? Huh? Anyone have any guess? Huh? Buntan? Come, like, what do you have? Huh? Diverge, ah? Why? 1 over 0. 0. What do you mean by 1 over 0? So it says the top grow faster than the bottom. Why? Or you just look at the graph, is it? Okay. There's one way you can see it, but you should make that precise because sometimes, right, if it grow not as fast, it still can be killed by the denominator. Okay. So how to make that precise? Okay. So we use the same trick. Okay. We use the same trick. We get rid of square root n this time. Okay. So we'll get rid of square root n this time. So let's get rid of square root n instead of n. Okay. Let's see why is this enough to see what we want to see. Okay. At the top, we got square root n. Okay, we still got n factors at the top. But at the bottom, we managed to reduce one term into convergent sequence. Okay. Can you see the convergent sequence inside the denominator? Anyone can see? Everyone? Can you see? What's the convergent sequence there? E n 2 over n. Okay? So 2 over n converge to where? No. 2 over n. Talk about 2 over n first. 0, right? Okay, because you can look at the continuous limit of 2 over x. Okay, 2 over x go to 0 when x go to infinity. So the discrete limit is also 0. So 2 over n go to 0. E, of course, go to e. So e plus 0 is e. Okay, you can see that the denominator converges to square root e. Okay, but what happened to the numerator? So the numerator will be just keep increasing. Okay, so the bottom converge, but the numerator diverge. Okay, so the denominator will converge to a finite number square root e, but the numerator diverge to infinity. Okay, so the conclusion is this sequence will diverge. Is there any way to make this sequence converge? Let's say you can change the sequence a bit. Can you make it converge or not? So following the idea just now, right? So just now we said that the numerator increase faster than the denominator. Unless you give enough power to the denominator to increase as well, so that you can decrease the whole term, right? Because now the bottom is going towards a constant. Okay, so if you increase the power of the denominator, probably you can make this sequence converge. Okay. Any question? No, huh? Okay, I'll repeat what I said again. So let's say we can change this sequence a bit. Can you, how do you make this sequence converge? Either you can increase the power of your denominator, or you increase the power of you decrease the power of your numerator, right? So just now our idea is the numerator grow faster than the denominator. So if you can reverse this, then you can make it converge. Okay. 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 Yeah, this yeah. No, I mean you can change if you can change the formula. You can put different factor into your sequence, then you can adjust it. Yeah. Okay. Okay, maybe I skip one of the question. Maybe we'll come back. Okay, there's one question, either I left as exercise or we will come back next time. Okay, so this is about the sequence ln n over n. Okay, so I left this as a homework. Maybe we'll come back as an exercise next time. We'll see. Left this as an exercise. Homework. Okay, so next, okay, we got third two now. Okay, so please write this down. We have a third two. So which we call a squeeze theorem. Squeeze. Yeah. Okay. So suppose you have two convergent sequence, both converging to the same number. Okay. Let's call it L. Okay. And you have another sequence get squished between AN and CN. Okay. For all n. Then you can find the limit of the middle sequence, which is also L. Okay, so this is the squeeze theorem. Okay, so P. So schematically, how does it look like? So let's plot this schematically. So let's say we got a AN, okay, maybe going up, increasing to an asymptote. Then we have another C and decreasing to the same asymptote. Got a BN, okay. Maybe this BN is quite jumpy, so jump up and down. But it always stay in between CN and AN. This is the condition. Okay. Then the limit, three of them will have the same limit. This is what the term said. Okay. Everyone got it? Got it? Okay, if you got it, I got one question. Let's say this BN, this BN, a bit naughty. Okay, this BN a bit naughty. So maybe in the first few terms, it jump outside the AN and CN, but it stay close or in between AN and CN after a finite term. Does this theorem still hold? Huh? Why? Does this theorem still hold? Because this theorem says that Bn have to be in between AN and CN for all n greater than some n. Huh? Does it still hold? Why? Why? How? How? So at the end is the key point of our limit. Okay. So we don't really care about a finite term, what happened before. Okay. We only care about infinite terms at the infinity. Okay. This is the key of limit. Okay. This is the key of limit. Finite term doesn't affect our limit. We only care about the infinite terms the terms at infinite. Okay, so you can see that this condition here is true for n that is greater than some n. Okay, as long as after some n it satisfies this condition, then it will work. Okay, limit only care about terms in infinity. Okay, so this is the key. Okay, so since we know this already, let's do example. So for example, can we find the limit of sine to the power 3n over n? Can we find the limit of this? Yeah, we want to use squeeze theorem. So how can we bound these two sequence here? Bound this sequence here. What sequence we need to find? Okay. -1 over n and 1 over n. So how to find these two, right? So we need to see whether we can bound any term inside this sequence or not. Okay. So one key things you must remember is we can bound cos and sine between 1 and -1. They won't jump away from 1 and -1. Okay. The only way to make this codomain bigger or larger is to scale the function itself. Otherwise, you will just stay in between -1 and 1. Okay? So note that sine n is in between 1 and -1. Okay? If you take cube of them, you still stay in -1 and 1. Okay? So in this case, we can bound our sequence sine cube over n by 1 over n minus 1 over n and bounded above by 1 over n. Okay. Oh. Greater than 1. Okay. So is this helpful or not? Squeeze theorem says what? You need to bound by two convergent sequence. Okay. They converge to the same place. Only you can make conclusion that the middle one also converge to the same number. Thus, the two bounding sequence here converge to the same place. Huh? They both converge to where? 0, right? Okay. So we know that. So how do we find the limit, discrete limit? We use the continuous limit. Okay. So we first need to understand the continuous limit first. Okay. The continuous limit of 1 over x is 0, right? So by theorem again, okay, the first ever theorem we learned today, by the theorem, the limit of the discrete sequence is also 0. Okay. And we also learned that if we multiply constant to this convergence sequence, what do we get? What's the property? We get minus the original convergent limit, okay, which is -1 times 0, which is just 0 again. Make sense? Okay, so this one is by and also property of limit of sequence. Okay, so we know that they are squeezed by two convergent sequence that converge to 0. Then we can conclude that by squeeze theorem, the limit of sine cube n over n is also 0. Okay, so you have how many things you need to check? You need to check that your sequence is bounded by two convergent sequence. okay, that converge to the same number. Only you can use the squeeze theorem. Okay, so actually, how does this graph looks like? Okay, actually, there's a real version of this squeeze theorem. So I will draw the real picture. The real picture. So sine cube over n should look something like this. See. Wait, let me start again. Okay, something like this. Okay, so this is the sine cube n over n. Okay, so where is 1 over n and minus 1 over n? Okay, so 1 over n should be somewhere here and here. Yes, here is 1 over n. And minus 1 over n is somewhere here and here. Okay, and then this question asks about positive part. So positive part is here. Okay, here. Okay, so you squeeze by two convergence sequence, and then this is like the now just now you say about damping, right? Yeah, this is a bit like the damping stuff. Okay, so you converge. Okay. Any question? Any question? Okay, keep going. Keep going. Okay, next we got a proposition. The proposition is if the absolute value converge to 0, okay, absolute value of your sequence converge to 0, then the original sequence also converge to 0. Okay. So just now we mentioned a concept, right? Actually, I don't care the oscillating. Okay, I only care whether the value close to the limit or not. Okay, this is exactly what it is trying to say. You take the absolute value. Okay, let's say all of them on the positive side. Okay, converge to 0. Then the original limit, which is alternating between the line y equals 0, also converge to 0. Okay, so maybe you don't believe it, okay, or you believe it. Okay, so we got an easy proof here, very quick one. Okay, there's not there's an easy proof here. We show you the usefulness of this squeeze theorem. Okay, we're going to use squeeze theorem and see this. Okay, not that this an is arbitrary sequence that satisfy those conditions. So a very quick proof. So we can bound this absolute value of an. We can bound our an by the absolute value of an. Okay, and bounded below by just taking the negative of absolute value of an. Does everyone get this? So you have your term, okay? You take your absolute value, right? So let's say, so for example, here is minus 2, then here will become 2, and then on the other side becomes minus 2. Okay, so this is always true, right? So this is an example. Okay. But not that, okay, not that one. Not that since we have a condition that the absolute value of an converge to 0, right? the left and the right also converge to 0, right? By the property of the limit of convergent sequence again. Because minus the absolute value of an is just a scalar multiply a convergent sequence, right? Okay. So limit of minus an equals to minus lim of the absolute value of an, which is just minus 1 times 0, which is 0. Okay. So you're squeezed by two sequence that is converging to 0. So by the squeeze theorem again, the middle sequence also converge to 0. So this demonstrates a nice result if we have some useful theorem or property. Okay. You don't need to check every example. I show this properties without having any examples. Any example that satisfies the condition will have the corresponding property just by using squeeze theorem and also property of the limit. Okay. 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 So if there's no example, maybe this thing is not useful. So let's take an example. So let's take an example how this get applied. So for example, okay, we all know 1 over square root n converge to 0 just now, right? This is what we found the first example, find the first example. Let's say I want to find the alternating version of this sequence. Okay, I let it alternate. Does it still converge? I let it alternate. Does it still converge? Huh? Right. So it still converge. Why? Because just now we say that. It says what? So what's the property we have? If the absolute value of the sequence converge to 0, then the original sequence also converge to 0. Okay, so what happens here? So we need to consider the lim to infinity of the absolute value of this thing, the sequence, which is just the 1 over square root n, which we found before is 0. Okay, so since this is true, so by proposition, we know that the alternating 1 over square root n, okay, the alternating 1 over square root n is also converging to 0. Okay. Okay. So if you don't want to go through this, right? If you don't want to go through this proposition, you also can go through squeeze theorem again. Okay. So you can go over again. So you can go over, maybe how about use another. So you could also, so this is the first, this is the second. You could also go over squeeze theorem again. Okay. And you can squeeze this sequence by, okay, you squeeze these two sequence. 1 over square root n and negative 1 over square root n. Okay. And then you can see that both 1 over square root n and minus 1 over square root n both converge to 0 and n go to infinity. So by squeeze theorem, it also converges to 0. Okay. Yeah. Really, number 2 is just number 1. Number 1 is also number 2. Okay, so number 2 show you how the proof go in number 1. Okay, using an example. Any question? Okay, maybe we stop here first because next example kind of be long. So any question before we break? Any question before we break? Take a break. Clear? Yeah? Yeah. Any question from the back? From the back? From the back? From the corner? From the corner? Any question? If not, then we will take a break until 10:03. Okay, 10:03. We'll come back for example.
可以，
没事，我知道你刚才问有人有问题，OK。
干嘛你不问？
没有，因为我觉得如果这样傻逼的问题就很打扰全班同学时间。
不会，
好了，就是
没有一个题目是傻的。
好，就是问一下这个我觉得它这个是能够推广，没关系，这个是能推广到其他的 constant 的，对不对？就是这个零陪任意 constant。但是我说最好，就是
没有错，没有错，非常好。对，因为如果你把这里调掉就可以了。
对啊。
对。
这样的话，那个负的 n 的话，那 diverge 的呀。
你的 n，
因为对。
有想一下哦，想一下啊，这样可能是不可以哦，看下哪里会出问题。
就只是说，如果它，因为它可以从这一步，它可以
没有，你 squeeze 就不能够用了，因为一个是去一，一个是去减一，你去到不一样的地方，你怎么用 squeeze
地方？哦，所以这个本质还是用 squeeze theorem 去推出来的。
对。
哦，所以如果用 squeeze theorem 的话，就这个东西它是不满足在这两个中间的。
不是你的 squeeze theorem 要两边都去同一个地方，但是如果你放弃其他 constant 的话，不是一个就去正的它，一个去负的它，那你就没有 squeeze theorem 那个条件。
哦，所以说其实这个是可以换成 constant， 但是就是这个负一的 n 它是两边是不一样的 constant， 所以就是错的，
就不能够用 squeeze theorem， 这样你不会有那个解。
老师就是它这个零是不能换成其他常数。
可以换成。
但是你就没有相同的结果。
零可以换成其他的。
不能换成其他常数。
一个如果正负，如果两个它们的极限都是同一个的话，你凭什么？
一个是一，一个是负一。
对，因为它是固定的。
没有，我意思说，对于两个就是它们极限是一样的话，
哎，不，就打个比方，负一的 n 次方，它趋近多少？负一的 n 次方，它的那个绝对值是一嘛，对不对嘛？那我问它趋近谁？负一的 n 次方。
我去想一下吧。好，然后
就
没有，你换了过后，你就不能够用这个 proof， 因为 squeeze theorem 不能用，明白吗？因为你一边是去正的它，一边去负的它。
哦。
就比如说负一的 n 次方，
你看一个去二，一个去减二嘛，但是 squeeze theorem 说这两个要一样嘛，他们去的里面。
诶。然后还有一个问题就是说，就是我刚刚听到有同学说是那个 numerator grow faster than denominator， 但实际上我觉得用这个方法来说是不可以来判断的吧，因为这不是绝对的呀。就是如果上面的它 grow faster than 下面的东西的话，就它不一定是，就它不一定是 converge， 不一定是对 diverge 的。
哦，一定的。
怎么可能啊？
求导，你求导也知道。
你自己看这个啊，你就举个这个例子，它上面是不是 grow faster 在下面嘛？
哪个？
没有，你根本就看不到我
这个，这个是下面 grow faster。
这个换成这个的话，
哦，你说反的哈？
对啊，
反的就不行啊。
对，所以我就说
没有，不是，
对，所以我觉得你讲的对，就是它要 fast 到一个程度，就是或者它要不够 fast，
就是所以说就是不是 true for all。
对，所以我就是说要 make precise 哦，因为有时候像你讲的，如果你真的进去看的时候，其实它也没有比它快多少，所以那时候还是有一个 limit， 但是如果它快到一个程度，它就会开始 diverge。
OK， 好，那我们再换一下，如果下面的它 grow faster， 那上面的话，它是 converge 的 for all situation 吗？
因为我们没有 map precise 什么叫 faster slower，所以我们没有好讨论这个问题。
哦，所以它也不是 true for all situation 的，也要 limit，不，也要去 precise 一点。
要 precise，对。
好的
所以
，thank
所以
you，thank you。
哎，我觉得在班上。
好，那耽误全班时间哦，别人会觉得我很傻逼了。这种简单的问题，
不会，你看这里的都很有兴趣。
我以为你说他们都觉得这题不傻逼。
他们都很有兴趣。
就是上次你跟我说你
呀
就是关于这个你放在就是有一页那个
对，
黑板单那个我没找到好像
没找到。
在哪里？你没找到，给我看一下。就是你是放在哪里？就是
你在哪个？
就是我就是这个里面我好像没找到，
这里 lecture 4哈，
那就4里面。
有吗？看一下，我应该更新了吧？啊，
看这个是吧？
我忘记了。
那是4号哦。哦，这也是 OK，谢老师。
我想问一下，之前不是有一个 Theorem 是这个吗？那所以如果我想要，就对于这些问题，我可以把它转换成一个方程，然后再用诺贝达法。
也是可以，可以的。
就是这两种方法都可以。
可以，没错。
我们在听问题了
啊，该听问题，可以。
对白要吃了不？对白要吃了不？那个我昨天本来要吃的，就吃了。明不喜欢吃面包的人，要吃面包。你那个什么吃的那个点心，那个是来调风的，拜。正好是那个小问题。我知道问题，有点 A，我要放你嘴。最近你家嘛，牛逼啊！别听话，牛逼嘛。老来讲，谁？
我要确认一下嘛，这个的意思就是，假如我们现在这个是0.001，
对，
还就是到一个灯的时候，它过后都会响过这个灯，就它过后
对，其实我还要再加多一个，对你讲的对，我还要加多一个 when n is large，呀，不止一个吧，我还要找更多，要找全部，
就确认全部都是
要全部
OK。
对，要全部。因为如果不全部的话，就像刚才讲的，就没有啊，就要全部。 Hello. I think let's come back. Where's one group of people?
看你们这边摇花。
start. Yeah.
我知道的。
你知道？
那要上课。
Okay. Okay, so next example is kind of crucial. You'll keep seeing this again and again and again. So make sure you know what is going on. So let's consider r to the power n. Okay, you fix an r in the real number. Okay, and then you take the power of this number. Okay, and then see when it converges. Okay, I want you to try an experiment now. Okay, try with, for example, r equals to minus 0.5, r equals to 2, r equals to 1, r equals to minus 2. Okay, see whether this sequence converge or diverge. Okay, so you need to take the power of this number and then see whether they converge or diverge. Then try this number. See whether the sequence you get converge or diverge. Okay. So you try R1 squared, R1 cubed, R1 to the so on. Okay. Try. Does everyone understand the sequence I'm talking about? Understand? Okay. So you fix an R, fix this four number, and then you take power of them. See whether the sequence converge or diverge. Okay, have you tried? Already? Okay, so we have a claim here. Let's see my claim and your experiment agree or not. Okay, so my claim here is if we consider every number in the real, okay, so when does the sequence converges? So it will converge only for R in between -1 and 1, doesn't include -1. Okay. Okay, so away from 1, greater than 1, it converges. Less than or equal to -1, it diverges. Okay, so in precise, what we want to say is what happened for, let me see. So let's following the order of our real line. So we break it into R less than or equal to -1, and then in between -1 and 1. Okay. And then R equals to, and then R equals to R greater than 1. Okay. And then you can see that 4 of these number fall in which category? Okay. Yeah, so what happened is less than -1, it diverges. Okay. And then in between -1 and 1, it converge. So converge to 0. When R equals to 1, it converge to 1. R greater than 1, it diverge. But it diverges to infinity. We put infinity here. Okay. So let's see. Maybe let's prove this claim. Okay, let's prove this claim. So we start from those that are easier to see first. So for example, when I equals to 0, okay, it should be obvious that this converges to 0. Okay, 0 to any power is just 0. So taking a limit of a constant sequence 0 is just 0. Okay. Everyone okay or not? Yeah. So how about R in between 0 and 1? Okay. So I think this is the geometric series, right? Or not? In between 0 and 1. So this is just 0. You should have seen this before. Okay. So why do we split up -1 to 0? Okay, because if you take point from -1 to 0, and then you take power, right? Odd power is minus, even power is, so it alternate positive. So we split it up. So we split it up and study it. Okay. But what? But the second line says that if we just consider the absolute value, it is just 0. Okay. So by the theorem before, we know that it is 0. But here there's another extra thing you need to consider. So the absolute value of Rn is equals to the absolute value of power of the absolute value of R. So you need to as this one with like. So we know that this is true. We also know that this is Rn is in between 0 and 1. Like n together with theorem or proposition. Just now we call it proposition before. the limit together with the proposition before the limit of Rn also equal to 0. Okay. Okay. So we settle the first, not first two. We settle the second one. Okay. So we still have some more to settle. Settle which one first? So maybe settle r equals to 1. Okay. So r equals to 1 is also easy. It's like r equals to 0. Okay. So you can see that why we split this number up. Okay, because if you take power of n, you still get back 1, or you get back 0. So we split this number up. Okay. So this is just 1. Okay, so next, let's deal with greater than 1 first, and then we will deal with less than equal to -1. So for r greater than 1, okay, actually this is also diverging. Okay, so why diverge? When I put by calculus 1, right, you should really think of it as the limit of the continuous function. The limit of the continuous function. Okay. You should see the graph, for example, 1.01 to the power n to the power x, or 2 to the power x, e to the power x. Okay, they all diverge to infinity. So why we split? Why we consider r less than -1 separately? Because it also alternate. Okay, this time it not only diverge, it alternate. So it's getting bigger, 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 bigger. So you should think of it like this. Okay, so let me draw for r greater than 1 case first. So r greater than 1 case is something like this. So I go to infinity. But if you put the minus factor in, so it will like growing larger and larger both way. Okay. So it doesn't diverge to infinity or just negative infinity. So we cannot find the limit. So we will say that the limit doesn't exist because it diverges both way. Okay. Everyone follow the logic. Okay. If you follow the logic, the main conclusion to make here is you need to remember that from -1 to 1, okay, not including -1, if you take the sequence of their power, they converge. Apart from this number, they diverge. Okay. So how you remember is only number like 0, negative 0.5, 0.5, 1, 0, they converge for the sequence of power term. Okay, so this is the conclusion you need to remember. You will always see this sequence, frequently see them. Okay. Any question? Any question? Okay, I think there's a next example in your notes. We will left this as homework, or either next time I will bring it up in the before the lecture. Okay. Okay, next. Keep going. Keep going. So let's keep going. Going. So theorem. Okay, next theorem. This theorem will speed up your answering. Okay. So let's say you have a sequence, converging sequence, okay? And your function f is continuous at L. Okay, so you regard your f as a continuous function. Then if you just look at the discrete domain of your function, okay, you put in your an, the limit of this guy converge to what we want. It's just f applied on the L, which is f on the limit of your sequence. Okay, start again. Okay, I repeat again. So let's say we have a sequence converging, and then our f is continuous. Then the limit of fan converge to fl. We can see that this limit here commute with our function. Okay, so the limit goes into the function. So actually, there's a name for this. This is called sequential continuity. Okay, so you take a sequence and then you check the continuity of your function. So how does this look like? So how does this look like? So let's plot a graph. So we will always plotting a graph for this. We have a we start with, so both of them are R. So we start with AN. Okay, AN. So AN, A1, A2, A3, A4, and then so on. It go closer, 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 and closer to a point. Call it L. Okay, everyone see this? Okay. So this is the first condition. So let us put those conditions together. Okay, they converge to one point, and then f is continuous at L. Okay, so what does it mean by f is continuous at L? So maybe you got an f like this. Okay, your f. Okay, now you consider what is f a1, okay, f a2, f a3, and then so on. Right? Okay, you see this sequence here. So you can see that this sequence, and then finally you reach FL. Okay, so a priori sequence here, right, doesn't need to converge to FL. Okay, but if your function is continuous, then the sequence here must converge to FL. Okay, otherwise, if it's not true, then your function is not continuous. Okay, make sense? Question. Explain again. From where? All over again. Which part? Okay, how do you mean? Okay. So this is this theorem here. So my argument is, let's say it doesn't equal, okay? Assume that it doesn't equal, okay? Then the contradiction is your function is not continuous. Yeah, this is an equivalent way to answer why it must equal. Or you mean why let's say it doesn't equal, why it implies it's not continuous? Okay, so if you take, okay, so this have to go back to your definition of continuity. So well, let me remind you the continuity statement. Okay, so your continuity statement got, I think, two parts. Okay, the first part is if you look at this point, so when we want to ask whether this function continuous at L or not. Okay, so this is the question. So question F is continuous at L or not. Okay. So by definition, if you go from the left, okay, and go from the right, okay, first of all, they should agree. Okay, and at the point itself, it is just that limit. Okay, so this is continuity. Okay, so this is the continuity. So let's say we take this AN, right? We take this AN. We approach, let's say we take this specific AN. We approach L from the left, okay? And this limit doesn't equal to the point on L. That means FL would jump somewhere outside. Okay? So the function jump is not continuous anymore. Okay. What does it do with convergence? What do you mean by that? Or you mean why this FAN converge? Precisely this limit tells you that it converges. The continuity implies the conversion of this sequence. Yeah. Yeah. So the continuity gives you the conversion. Yeah. Yeah. Continuity gives you a conversion. Yeah. For free. Okay. Okay. So let's see how to use this. Okay. Let's see how to use this. So example. Okay, let's take an example. So let's find the limit of sine pi over n. Okay. So sine pi over n. So really, what's the function we are looking for here? What's the function? Yeah, what's the continuous function that relates to this sequence here? Sine, right? Sine x, right? Okay. So we should look at sine x equal to sine x. Okay. So sine x is continuous or not? Yes, sine x is continuous, right? So it means that we should look at the sequence of pi over n first. Okay. So what does this sequence converge to or diverge? Converge or diverge? This one. Converge, right? Okay. This is just equals to pi of lim n over n. Okay, because we know that lim x to infinity over x go to 0. We know the continuous limit of 1 over n, then we know the discrete limit, which is pi times 0, which is 0. Okay, everyone follow here? This is just repeating what we did just now. Okay, so you got a sequence pi over n converge to 0. Okay, so you should have in your mind this sequence here. Okay, you start with pi and pi over 2, pi over 3, okay? And then you converge to 0. Okay, now you got sine. Sine function, you should be very pro at sketching it now, right? Keep doing the polar graph. So the sine function should be looking like this. Right? Okay, so you can see that sine x is continuous at 0. Okay, so just now we say that we can use this continuity to find our limit. Okay, we can use continuity to find our limit. So since fx equal to sine x is continuous at where? Where? At pi over n or at 0? 0, right? Okay. We only care about the limit point. Okay, s equals 0. Since it is continuous at 0, so the limit of sine of pi over n is equal to sine of limit n to infinity over n. Okay, so this is by theorem just now. Okay, since it is continuous, we can bring the limit in. Continuous at the limit point of your an. We can bring the limit in, and then we will evaluate this number sine 0, which is 0. Okay, from the picture, you also can see that it converges to 0. Yeah. Okay, so there's one idea I want you to keep remembering. We are getting help from a continuous function to find discrete limit. Okay, so although we find stuff on continuous function, but what we get is the limit of discrete sequence. Okay, I want you to differentiate these two. One is continuous function, one is discrete function. You need to differentiate these two. Okay, so that you won't confuse. You'll see that I always draw this real number, continuous real function, but really what we care about is this discrete point. Okay, any question? Any question? Question. Please ask if you got any silly question. Because silly question will help you to understand. Silly. Any question? Question? No? Everyone follow? Everyone follow? Okay. Everyone follow? Okay. Sure. Okay, next. We're gonna introduce how many things we introduced today already? How many property we have introduced? So first, please write down in your cheat sheet. So first, we can find discrete limit using continuous limit. Okay. Second, we can build new convergence sequence using all convergence sequence, which we can add them, multiply them, or multiply by a scalar, or addition, right? So we can find the limit. And then third, what do we have? We have squeeze theorem. Okay. And then next, we're going to introduce a theorem called monotonic sequence theorem. But before doing that, we need to introduce some definition. we need to characterize our sequence. So let's characterize our sequence. So a sequence is increasing. Okay. When we say a sequence is increasing, if an is strictly less than an plus 1 for all n, or an plus 1 is greater than an. So the next term is greater than the previous term. Okay, strictly, strictly. And then decreasing, okay, decreasing if an is greater than an plus 1. Okay, so the previous term is greater than the next term. So it's decreasing. And then we also have idea of non-increase. Okay, let's do non-decreasing first. So non-decreasing, okay, if an is less than or equal to an plus 1 for all n. So you can have equal or increase. So non-increasing mean either you decrease or you can have equal at some stage. Okay, so you can see that these are quite algebraic, right? So you also can think of it geometrically. So increasing will be something like a slanted path going up, going upward. Decreasing will be going downward. Increasing will be going downward. And non-increasing will be like a staircase. You go up, and then maybe you stay constant, you go up, stay constant, go up, stay constant. And then non-increasing will be going down, maybe you stay constant for a while, and then going down, stay constant for a while. Okay? Okay. Okay. So next. A sequence is strictly monotonic sequence if it is increasing or decreasing. Okay. So the strictly here will infer to the strict inequalities. Okay. And we'll just say that it is monotonic sequence if it is non-increasing or non-decreasing. Okay. Let me move a little bit. Okay. So strictly monotone, we will say increasing or decreasing. Monotone means non-increasing and decreasing. Okay. Please bear with me for a moment. I need the third definition. Only we can put these three together to form the theorem. Okay. So a sequence is bounded above. It's bounded above if there's a number such that, okay, every number is less than m for all n greater than 1. Okay, you can bound above, or similarly you can bound below. Okay, so you can bound below if there exists another number called little m such that every term in the sequence is greater or equal to little m for all n greater than equal. Okay, and we say that a sequence is bounded if it is bounded above and below. Okay. So if you are bounded above and below, then you are bounded. Okay. So now what do we have? What do we have? So we have increasing sequence or decreasing sequence. And then we have bounded sequence. So we're trying to put all these ideas together to get a convergent sequence. So the theorem is, so the theorem we want to get is monotonic sequence theorem. So the statement is every bounded monotonic sequence is convergent. Okay, so try to think about this for a while. Every bounded monotonic sequence is convergent. Can you find any counterexample or any example that make you don't believe? First, convince yourself whether you believe or don't believe first. Yeah, if you believe so, why is it true? What is this, huh? Okay, sure. What is this? So maybe we take one of the staircase, right? So let's take some of them. So we take one of the staircase. So what this says that is you need to satisfy these two conditions, then only you will get convergent sequence. Okay. So what does this two condition means? So monotonic. What is monotonic? Either you are non-increasing or non-decreasing. Okay. So there are two pictures you have. So either you going down or either you going up. So bounded mean what? Yeah, bounded above and bounded below. So for every term, you should have some bound. You can bounded above and bounded below. Bounded above and bounded below. Okay? But you should imagine our sequence, right, is keep going on one. You can only keep increasing or keep decreasing or keep equaling. Okay? So you got a door. You got a door. But you keep moving forward to the door. Will you hit the door or not? What? You open the door. Okay, I mean the door is not open. The door cannot open. You don't have the key. Okay, you cannot open. Right. So you keep moving toward the wall. Okay, the wall. Yeah. Okay. Will you hit the wall? You will definitely hit the wall, right? Okay. But hitting the wall here doesn't mean it has to be equal. It can be like approaching asymptotically. Okay, right? Because this is the property of real number. Yeah, real number have this property. You can forever going close to the person, but you can never touch. Okay? Yeah. Okay. So you can go forever close to the wall, but you cannot touch the wall. Okay. Okay. So you guys more towards real life example. Okay. Let me see. Okay, any question? Quick go question, then we after the question we dismiss. What? What? What you mean? You don't touch how to converge? What's the question? Wait, listen to what he said. Yeah. How to combine? Cannot combine. If bounded sequence then converge. No, bounded and monotone. Bounded. He saying that there's because there are two bounded stuff, right? So you cannot reach both. You only can reach one of them. Depend on you are decreasing or increasing. Yeah. Okay. So if you are decreasing, you bounded below, then must converge. If you are increasing, bounded above, then you just hit the wall. Or go very close to the wall. Convergence will equal to the wall, but approach. Meaning the limit won't happen inside your sequence, but you will limit to that, you will converge to that limit. Yeah, the limit itself won't be the term inside your sequence. You are just approaching it. For example, just now, right? 1.01, 1.001, 1.0001. There's no 1 inside my sequence, but it converts to 1. What do you mean? Depend on your sequence. Bounded what value? Depend on your sequence. The value will depend on your sequence. Okay. Second. Not necessarily. Okay, so there's a question here. So let's say this is decreasing, right? Okay. So one obvious bounded above value will be just A1, no? Okay. So you cannot simply pick this wall, right? Let's say it already converged here. This is the bounded below. You also can pick something lower, right? It's still bounded below by this green line, but it doesn't converge to that. Okay, so the limit is still something you need to work on. Okay, to find the limit. Yeah. So you cannot just say that it's bounded below by this green line, so it converges to this green line. Right? Make sense? Okay. So you still need to make an effort to find which bound is really the limit. Okay. The limit will be the bound for sure. Okay. And the limit will be the bound. The bound might not be the limit. Okay. Yeah. The limit must be the bound. The bound might not be the limit. Yeah, make sense? Make sense, huh? Yes. Yes. Okay. Okay, see you on Thursday. Okay, Thursday.